Okay, thanks for the introduction and thanks for the organizers giving me this opportunity to have a talk here. The title of my talk is the first Hochschild cohomology groups on the gluings, and this is a joint work with Rubio and Lleonard, Rubio, and Degrassi. Now let's start. My talk will divide into two parts. One is for the Hochschild cohomology groups and another is about our main results. And I will introduce our main results from gluing vertices and gluing arrows. Here, let's fix their notations first. Let K be their ground field and Qi be their bound quiver, and let B be the set of all finite passes in their quiver Q, and it obviously gives their K basis of their path algebra KQ, and let AB be finite dimensional quiver algebras of their form KQ quotient and idea I. Where for the Hochschild cohomology groups, their nth Hochschild cohomology group of an algebra A denoted by HHN of A is defined by their nth extension of A over its enveloping algebra. And there are some well-known facts about their Hochschild cohomology groups. The first Hochschild cohomology group of an algebra is isomorphic to the space of derivation quotient by the space of inner derivation. And in particular, HH1 is a Lie algebra with the brackets induced by their commutator. And it's well known that the Hochschild cohomology group is an important invariant. More precisely, the derived equivalence preserves HHN for each degree, and stable equivalence of Morita type preserves HHN for each positive degree. Now let B be obtained from A by gluing two vertices in the quiver of A. If we glue a source and a sink, then A and B are stably equivalent but not of Morita type. But it's a stable equivalence very close to the stable equivalence of Morita type. Since stable equivalence of Morita type preserves Hochschild cohomology groups of positive degrees, then a natural question appears: what is the relation between HHN of A and HHN of B if we glue a source and a sink from A to get B? And more generally, how about if we glue two arbitrary vertices? In this talk, I will give the answers of the above questions when n equals to 1 for any finite dimensional quiver algebras. Before showing the approach to compute HH1, let's recall the global basis theorem and parallel passes for the quiver algebra. Let's fix an admissible real order on the basis, and for each element in the path algebra KQ, its tip is the maximum monomial appearing with non-zero coefficients in this element. And for each non-empty subset X of the path algebra KQ, we put tip X to be the set of all elements tip R for each non-zero element R in X. And our global basis of the idea I with respect to the admissible real order is the subset G of I such that tip G and tip I generates the same idea. And we call two passes alpha and beta of the quiver Q are parallel if their starting vertices are the same, and similarly for their ending vertices. And if X and Y are sets of passes of the quiver Q, we denote by X parallel Y to be the set of all elements of the form alpha parallel beta with alpha in X and beta in Y, and let Kx parallel Y be the K vector space with basis X parallel Y. Where in 1997, Bardzell gives a minimal projective resolution of an algebra, and it can be written in the following way: use the reduced global basis, where the differentials d1, d0, and mu are given by the following formulas. And we apply their home functor home blank A over its enveloping algebra, and using some canonic isomorphism, then we can interpret the above complex to be the following complex using the parallel passes, where the differential delta 0, delta 1 can be written in the following formulas. And there is a canonic Lie bracket using the parallel passes. And we have HH1 is isomorphic to kernel delta 1 quotient by image delta 0 as Lie algebras. Now let's go to our main results. For gluing vertices, we have the following theorem. Let A be a quiver algebra and B be obtained from A by gluing a source vertex E1 and a sink vertex En in the quiver of A. Then if E1 and En are from different blocks of A, then there is a Lie algebra isomorphism between HH1. But if they are from the same block, then HH1 of A is isomorphic to HH1 of B quotient by one-dimensionally ideal as the algebras. And moreover, if A is a monomial algebra and the characteristic of K is 0, then the one-dimensionally ideal lies in the center of HH1 of B, and we have HH1 of B is isomorphic to HH1 of A times this one-dimensionally ideal as the algebras. Now let B be obtained from A by gluing two arbitrary vertices. Then we can provide explicit formula between dimensions of HH1 of A and HH1 of B in terms of some combinatory datum. Now let's give you an example to show our main result. The quiver of A is given by this form, and E1 is their source vertex and E4 is their sink vertex. Now we glue E1 and E4 to get the quiver of B, and the relation of A is given by alpha beta minus gamma eta. And after gluing, the new relations are given by all passes of length 2 through F1, and the relation of B is given by the relation of A with these new relations. Now we fix an order on the arrows of the quiver of A by eta greater than gamma greater than beta than alpha. It follows that the global basis of A is given by gamma eta minus alpha beta. And the global basis of B is given by the global basis of A with these new relations. And we can show that HH1 of A is 0 and HH1 of B is isomorphic to K. Where for gluing arrows, we are particularly interested in the case of gluing a source arrow and a sink arrow. So what's the meaning of source arrow and sink arrow? We define an arrow alpha is a source arrow if the following two conditions are satisfied. Firstly, we require that the starting vertex of this arrow alpha is the source vertex. And secondly, except alpha, there is neither an arrow starting from the starting vertex, nor an arrow ending at the ending vertex. In other words, alpha is the unique arrow from the starting vertex to the ending vertex. Ideally, we can define the sink arrow. Where for gluing arrows, we have the following theorem, which is very similar to the gluing vertices case. Let A be a monomial algebra and B be obtained from A by gluing a source arrow alpha and a sink arrow beta. Then if alpha and beta are from different blocks, then there is a Lie algebra isomorphism between HH1. But if they are from the same block, then HH1 of A is isomorphic to HH1 of B, quotient by one-dimensionally ideal as Lie algebras. Moreover, if the characteristic of K is 0, then the one-dimensionally ideal lies in the center of HH1 of B, and we have HH1 of B is isomorphic to HH1 of A times this one-dimensionally ideal. Now let's end with an example. The quiver of A is given by A4, and alpha is the source arrow, beta is the sink arrow. Now we glue alpha and beta to get the quiver of B. So what we do the following three operations. Firstly, we glue the starting vertices of alpha and beta. That is, we glue E1 and E3 to get F1. Secondly, we glue the ending vertices of alpha and beta. That is, we glue E2 and E4 to get F2. And finally, we identify alpha and beta to get gamma star. Here, there is no relation for A, but all new relations are given by the newly formed passes of length 2 through F1 and F2, and all newly formed passes of length 3 through gamma star. In this example, the relation of B is given by one element, eta star, gamma star, and eta star. And a direct computation shows that HH1 of A is 0, and HH1 of B is generated by one element, gamma star per gamma star. Hence, we have HH1 of B is isomorphic to HH1 of A times K as the algebras. Okay, that's all that I want to say. Thanks for your listening.